Good morning, everyone. Today, our team, consisting of Van, will be presenting our credit risk modeling project. We've been working on predicting the probability of default, loss given default, and exposure at default for lending clubs' loan data. This project is a crucial part of our AI and automation in finance course at SP Jain. Let's begin this insightful journey.
Credit defaults pose significant risks to financial institutions. A borrower's failure to repay can result in substantial losses. Accurate risk assessment is vital to prevent crises like the 2008 subprime mortgage debacle. Our project seeks to develop a robust model to predict loan defaults. This model will assist lenders in making informed decisions. Our dataset comprises over 800,000 consumer loans from Lending Club. We utilized the Lending Club Loan Data Dataset, a widely used dataset in credit risk modeling. We used the expanded dataset containing loans issued from 2007 to 2018, providing a comprehensive historical perspective. This dataset includes various features such as loan amount, term, interest rate, borrower's grade, employment length, and more. Our target variable, good-bad, was derived from the loan status column, classifying loans into good or bad based on whether they were fully paid, current, or defaulted. Data preprocessing is crucial for model accuracy. Our first step was to clean and prepare the data. We started by addressing missing values. Columns with over 80% missing values were dropped. For others, we used mean or median imputation for numerical features and created missing categories for categorical ones. We also dropped columns that were initially deemed irrelevant based on our understanding of the data. For instance, we filled missing values in annual inc with the mean. And for imps since last delinq, we created a missing category. Identifying predictive variables is key to model success. We used p-values to assess statistical significance. Features with at least one significant dummy variable were retained. Non-significant features were dropped to streamline the model. This selection process refines the model's focus on impactful variables. Next, we engineered some new features and transformed existing ones. We converted emp length to a numerical variable emp length int. Similarly, we transformed earliest car line into emps since earliest car line to represent the number of months since the borrower's earliest credit line. We also converted term and issue D into numerical representations. Importantly, we addressed an issue with dates before 1969, ensuring accurate calculations for emps since earliest cur line. To make our data suitable for logistic regression, we created dummy variables. For categorical features, we used one-hot encoding. For continuous features, we employed a two-step process: fine classing and coarse classing. Fine classing involved dividing the continuous variable into many bins using pd.cut. Then, we used weight of evidence, WOE, and information value, IV, to guide the grouping of these bins into fewer, more meaningful categories. WOE helps us understand the predictive power of each category relative to the target variable, while IV measures the overall predictive power of the feature after grouping. We visualize this process using plot by WO function. For instance, with annual inc, we created categories like less than 20K, 20K, 30K, and so on. With emps since last delinq, we created categories like missing, 03, 430, based on their respective WOEs. After creating numerous dummy variables, we needed to select the most relevant ones for our model. We used p-values, a statistical measure of significance, to guide this selection. We retained features with at least one dummy variable having a p-value less than 0.05. Based on this, we dropped features like delinq, 2YRs, open ASCC, pubrec, total ACC, and total rev high lim as none of their dummy variables were statistically significant. With our pre-processed data and selected features, we trained a logistic regression model to predict the probability of default. We used a custom class, logistic regression with p-values, to obtain p-values alongside the model's coefficients. This model, named logreg3, was trained on our training dataset, and the resulting coefficients and p-values are displayed in this summary table. Model evaluation is critical to ensure reliability. Initially, a 0.5 threshold resulted in misclassifications. We used the ROC curve to find an optimal threshold. This threshold improved the model's accuracy. The ROC curve and AUC score provide a comprehensive performance evaluation. With our pre-processed data and selected features, we trained a logistic regression model to predict the probability of default. We used a custom class, logistic regression with p-values, to obtain p-values alongside the model's coefficients. This model, named logreg3, was trained on our training dataset and the resulting coefficients, and we evaluated our PD model on the test set. Initially, using a threshold of 0.5, we observed a significant number of misclassifications, particularly for bad loans. To improve this, we used the ROC curve to find the optimal threshold that maximizes the difference between true positive rate and false positive rate. This optimal threshold was found to be approximately 0.896. Using this new threshold, the model's accuracy improved slightly. The ROC curve and AUC score provide a more comprehensive evaluation of the model's performance across different thresholds. P-values are displayed in this summary table. Our model can predict defaults for individual loans. We demonstrated this with a sample loan from the test set. By applying the model's coefficients, we calculated the default probability. This manual calculation matched the model's prediction. It confirms the model's accuracy and practical application. Finally, we demonstrated how to apply the trained PD model to predict the probability of default for individual loans. By selecting a sample loan from the test set, identifying the relevant features, and applying the model's coefficients, we can manually calculate the probability of default. This manual calculation closely matches the probability predicted by our model, confirming the model's accuracy. We explored loss given default and exposure at default. A two-stage approach was used for LGD. Logistic regression predicted zero recovery rates, followed by linear regression. EAD prediction employed a linear regression model. These models complement the PD model for comprehensive risk assessment. Moving on to loss given default and exposure at default. For LGD, we employed a two-stage approach. First, a logistic regression model predicts whether a recovery rate will be zero or not. Then, a linear regression model predicts the actual recovery rate for cases where it's not zero. For EAD, we used a linear regression model to predict the credit conversion factor. The code for both LGD and EAD models is available in the LGD EAD models IPYNB notebook. Finally, we combined the predictions from our PD, LGD, and EAD models to calculate the expected loss. We applied the models to our test set, computed the EL for each loan, and then summed them up to get the total expected loss for the entire portfolio. We also calculated the EL rate, which is the total expected loss divided by the total funded amount. In our case, the EL rate was around 7.5%, which falls within the acceptable range suggested by Basel II. In conclusion, we successfully built a credit risk model that predicts the probability of default, loss given default, and exposure at default for lending club loans. Our model achieved reasonable accuracy and provided insights into the key factors influencing loan defaults. However, there's always room for improvement. Future work could involve exploring more sophisticated models, incorporating additional features, and fine-tuning hyperparameters. Additionally, Addressing the class imbalance issue could further enhance the model's performance. This project demonstrates the power of AI and machine learning in assessing and managing credit risk. Thank you for joining us on this credit risk modeling journey. I hope you gained valuable insights into predicting loan defaults. If you have any questions, feel free to reach out. I look forward to further discussions on enhancing financial risk management. Until next time, goodbye.